Welcome to the module devoted to encryption and mechanisms implemented directly by Windows that allow data encryption. We start from how the operating system protects the confidentiality of critical data, for example, various types of credentials. Above all, we have two clipboards for data. Data Protection API is a Windows subsystem responsible for security. It protects both user data, each user in a separate storage, and the computer itself. Let's see how it looks for keys. Secure communication using SSL protocol or secure communications using a secure version of Internet Protocol or IPsec require secure key storage. Keys are stored locally on the system drive. They are not, however, stored in plain text, but encrypted. To encrypt something, you need to have the key that encrypts it and later decrypts it. In this case, it's the Data Protection API, DP API, key. On the same level as the DP API, there's the Security Account Manager database, the SAM file if we're talking about a local computer, or the Active Directory database if we're talking about domain controllers, as well as LSA, Local Security Authority Subsystem Security Secrets. LSA secrets include account passwords used to start system services. If the computer is a domain controller, when it promotes this role, we need to give the password of the local administrative account. On domain controllers, there are no de facto local accounts. It's difficult to imagine running a domain controller while not running the domain at the same time. If different errors or inconsistencies appear in the Active Directory database, the safe mode must be available. In the safe mode, we log on to the account with the appropriate password. Secrets of that level are then encrypted with a start key, whose location we can configure using a syskey program. By default, it's stored in the registry on a hard disk drive, where Windows is installed. We can also transfer it to a floppy disk. Then this disk would need to be connected to the system during startup. It can also be derived from the password that Windows asks for during login. In regards to the user, the situation is very similar. The user may have, for example, EFS keys. We'll talk about them in this module. In other words, encrypting file system keys. A user may also have keys that allow a safe exchange of data by email. In other words, S/MIME protocol keys. These keys are stored locally. By default, they are protected by DP API keys on the user account, not on the computer account. On the same level, there's a user's profile data. This level is also protected with a start key. The result is such that if we have the startup key, we have access to data from the SAM file level. If, however, we have the DP API key, we automatically have access to the SSL and IPsec keys. Everything is encrypted, but the user does not need to provide any decryption keys. The default configuration is fully automatic. Though the configuration is automatic, it does not mean that it is absolutely safe. The purpose of the encryption is to guarantee the confidentiality of data. Someone who is not familiar with encrypted messages may haphazardly change it. The ciphertext can always be changed. In the simplest case, you can delete it. We've seen that programs work in this way to allow resetting the local administrator password. If we wanted to encrypt all the data we've talked about earlier, plus everything on the computer disk, we would need to encrypt the entire disk. At this point, several problems appear. One of the immutable principles of computer security states that the ciphertext is only as safe as the key used to decrypt it. Once we encrypt the entire disk, where will we write the key to decrypt it? This is the first problem. The strength of the ciphertext depends on the way in which we encrypt the data. As end users, we don't have much impact on this. However, we can always consciously choose the algorithm. The strength of the ciphertext depends on the length of the key. This is not a proportional relationship. Generally, however, a longer key improves the safety of the ciphertext. It's not that a key which is 2 times longer will give us 2 times higher security, but we will be a little safer. Disk encryption uses symmetric algorithms. They do not allow data encryption of any length. They only allow encrypted data blocks with a strictly defined length. If we use the same algorithm to encrypt many successive blocks, it turns out that the ciphertext is very easy to break, even if the key was long and the algorithm secure. Here we're talking about cryptographic systems and in particular block cipher modes. When selecting the method of encrypting the disk, we need not only to deliberately choose the algorithm and key length, but also the block cipher mode, if we have such. In the case of BitLocker and TrueCrypt, this can be selected. If we encrypt disks, we need to use solutions that when saving, automatically encrypt each sector, meaning 512 bytes of disk space. The solution also needs to automatically decrypt sectors while reading. It would also be good that during the entire encryption and decryption, computer performance would not visibly be reduced. When designing BitLocker, which was quite a few years ago, it was assumed that when reading a single byte, the processor can execute from 50 to 100 individual instructions, or cycles. Therefore, the assumption was adopted that the encryption of 1 byte data units cannot burden the processor with more than 35 cycles. BitLocker uses the AES algorithm to encrypt a single chunk of data, which requires about 20 processor cycles. This means that it's in the range even for computers produced 5 years ago. Since we're deciding on data encryption, we should be certain not only as to its confidentiality, but also its authenticity. Ensuring the authenticity of encrypted data on the entire disk is relatively difficult. Most often, the method used is attaching a signature to the ciphertext. At the same time, this indicates whether someone has changed the ciphertext or not. In the case of encrypting the entire disk, this is not an option, because where will the signature be saved? Some intermediate solution needs to be adopted. A haphazard change to the ciphertext needs to be more difficult. How can this be done? Diffusion can be applied, in other words, a diffuser. It works so that a change of 1 byte in the sector will cause a pseudo-random change of a large number of bytes in other sectors. The effect will be as such that if someone suspects that at a certain place in the ciphertext there's a SAM file, and tries to reset the administrator password by deleting the corresponding ciphertext bytes, then the contents of many files of the operating system will automatically be changed. The result will be that the system will not boot at all. That's why in addition to the AES algorithm in BitLocker, an original algorithm by Microsoft Research is used, which is called diffuser. It requires about 10 cycles for diffusing 1 byte. The result is such that for today's computers, the activation of the almost invisible protection of the entire hard disk drive is connected with a reduction of efficiency of about 5%. That's all concerning the basis of cryptography and data security. Encrypted disks must be managed in some way, especially in companies. We need to have the possibility of remote administration and remote program configuration that will encrypt and decrypt data. After all, we will not do it to each computer separately. In addition, some embedded emergency mode is mandatory. What do you do in a situation when a user we encrypted data for, or the user encrypted the entire disk himself, forgets a password? For example, the password that allows him to decrypt the disk. There must be some way to decrypt data on the disk on behalf of the user. Of course, this affects security because it's based on trust to the administrator. Additional benefits of programs that encrypt the disks could be something like hiding the fact of the presence of data on the disk. This is something that has not been implemented in BitLocker. This is something that makes TrueCrypt stand out as compared to BitLocker. TrueCrypt has such functionality that when one disk is encrypted, it will create a second disk encrypted with a different key. Since both these disks are encrypted, the analysis of these disks' content, for example when the computer is off, does not show any difference between one encrypted disk and the other. In general, it should be maximum pseudo-random data. Now, if someone asks us to decrypt a disk, in most cases those who are authorized to do so, such as the police, if they ask us, we have the obligation to reveal to them the password for this type of security. If we have the password to one disk, it will be decrypted and its content made available. If, however, we don't give a second password, everything that was encrypted and was on the internal hard disk will remain invisible, at least in theory. An additional advantage to disk encryption could also be checking the integrity of the computer. This function is only available in BitLocker and is not available in TrueCrypt. Its idea is that interference in the computer, for example moving the hard disk or a change in the order of the starting devices, causes automatic blocking of the encrypted disk. We've already mentioned authenticity. We said that a signature is used for it. However, in the case of disks, that's not possible since the sector has a fixed sector size. We can't force manufacturers of hard disks and low-level software to reserve for us a few extra bytes in each sector. We also can't write checksums to another sector, since there are programs that are based on the fact that sectors are independent of each other. Examples of such programs are database servers, which in their own way manage writing and reading. It cannot be that a change in data in one sector causes their automatic change in another sector. This is what would happen if a checksum were there. We could solve the problem by artificially doubling the size of the sector. Then all the problems are solved. We have a lot of space for the checksum. In addition, the operating system sees only half of the sectors and there are no relationship between the sectors. Unfortunately, we'd have to convince users that when buying, for example, a 500 gigabyte disk, it really has to be 250 gigabytes. We could meet some resistance. Therefore, disk encryption software, instead of using MAC signatures, broadcasts bits on as many sectors as possible. In addition to encryption, specific sectors use keys to avoid simple mathematic relationship. Well then,